we have the professor, I don't know how to say your last name, Juhani. Telling us about the FinReactor.
Right, good afternoon. Juhani Hyvärinen is the name. Right, and I'm professor of nuclear engineering in Lappeenranta University of Technology. And thanks, Rauli, for invitation. It's nice to be here. And it's the job of the universities is to think out of the box. So that's what we do. And I'll talk about purely heating reactors now today, because as you have seen, there are already plenty of electricity producing and cogeneration products on the market. But there is also some demand for heating only. So there is a need for heat. Space heating in our country, which is in population-wise small country, geographically large, but population is relatively small. We emit something like 5 to 10 megatons of carbon dioxide annually, and this is much more than electricity production emits these days. So this is the next biggest potential where we can do some good for the benefit of the climate. And the district heating networks already exist, as Rauli has explained in his reports, that almost all over the country, something like probably nearly 90% of the population has access to district heating networks, and they require heat at a relatively low temperature. Relatively low temperature, something like 90 to 120 degrees centigrade, which from reactor engineering point of view is very nice, because you can design a heating reactor to be low pressure, low temperature, and consequently low risk also. It's much easier to design it for low risk. And luckily there are not many people around the world who want to live in latitudes like ours. Okay, so the district heating market is limited to the Nordic countries and Russia, maybe parts of Canada and so on. But luckily the same temperature range is applicable for other uses also. District cooling in the summertime, when there is little demand for heating, there is increased demand for district cooling, and in this town, for example, or in this city, the municipal power company sells cooling also. So they have built, in addition to the district heating network, a district cooling network. And you can buy coal in the summertime, and it's, I understand, a rather successful product. And then, of course, desalination has been mentioned many times over. So there is some potential for global market if we can develop something which is, let's say, cost-effective and easily understandable. So that's what we set out to do. Here's just some numbers, a little more up to date than Rauli. Yesterday when I was coming to Helsinki, I updated this on the train. Finland, there has been some discussion today about public acceptance, and there seems to be some caution or some let's say fear that the public would be difficult to deal with, and it's a challenge. Okay, admitted, but I submit that the Finnish society by and large is ready for nuclear decentralization, and I'm basing my claim on the fact that we have just recently done this, okay, with a big power plant project, and which is the Hanhikivi plant up here in north. Hanhikivi was chosen out of 2 candidates. There was another candidate up here, Simo. And these two municipalities were actually competing to get the project. And I have seen grown men weep when their location loses the chance of getting a nuclear power plant on their side. I have actually seen this happen. So I would like to make them happy again. Also, I'm not sure if I'm the right guy. Maybe it would have to be somebody else, because I caused them a big disappointment up there. But then anyway, cogeneration and district heating, they have to be, when you want to provide heat, it has to be brought closer to the customer. So you can't transport it from one side of the country to the other like you transport electricity. And this creates the possibility that some of the bigger towns like Turku or Tampere or Vantaa or Espoo or Oulu, which in due course will have to renew their district heating supplies, might be able to consider, or Jyväskylä, or Joensuu, or Kuopio, or maybe Vaasa. Vaasa probably a little bit of a challenge due to local specific cultural features in other in plain language, the Swedish-speaking population who have a fairly big fraction in there and who are somewhat concerned from time to time about the language ratio. Being in the area also. Or my own town, Lappeenranta, might also. So I'm not aware of any of these cities actually having made any commitments or any comments or expressed any, let's say, strong explicit expressions of interest. But these are the people who would be first in the line, who would need this type of a product. And you will notice an important thing, that there are quite many inland sites here. There are quite many inland sites. Just the other day I had the occasion to read the Stux YVL guide, the regulatory requirements for external threats. And external threats, they write a lot about the loss of ultimate heat sink, and the loss of ultimate heat, the ultimate heat sink that they talk about is always seawater. Seawater, access to seawater, supply of seawater, stopping the seawater supply. So I need to put a question to them that could it possibly be also lake water or maybe atmosphere or even something else. Right, and the product, the heating product needs to be plug and play compatible with the existing heat source. So the population centers that we have are quite small. So this is actually in the number of you can read of the chart, the thousands of people living. So mostly Finns live in towns less than 100,000 people. And if you want to supply them with reactors, then 24 megawatts is rather nicely when you compare that to the number of thousands of people living, you will see that there are rather nice steps of about 24 megawatts. So it's not a coincidence that this 24 megawatts has been mentioned earlier today. And another benefit that you get out of such a small size, which is 10 times smaller than, or more than anybody else has been talking, is that even in Finland, just domestically, you get a potential for up to something like 70 units. So there would be a genuine fleet effect. Okay, this is very, very important for the practicability and for the competitiveness of such a product. And there would be a sizable number of larger reactors also, something like 10. The 70, I think, in Rauli's presentation, I think the numbers added up to 69, but then you were a little bit more modest in your conclusions. That maybe we should start from, I don't remember what, 20 or 30 or... But anyway, that's already a fair number. So there is a large domestic fleet effect that's possible. And relatively low temperature, low pressure, as already mentioned, which means that component manufacture domestically should be possible. So this should not be too difficult components to do in Finland by the Finnish industries. And in order to simplify life, our life and my former colleagues, the regulators' life, as well, familiar light water reactor technologies, materials, fuel would be applied. Okay, so those would be readily available on the market, starting from the fuel rods, maybe even fuel bundles. And I'm bold enough to say that no waste problems. I should have qualified that, no technical waste problems, because there may be some commercial discussions around that. But as was already pointed out before the lunch, there is all the let's say, everything that needs to be done in terms of nuclear waste management for light water reactors, we already have. So it's just a matter of licensing, allowing these things to be done, and companies willing to sell these services at a reasonable price. So, and other final, my main hobby horse really, other simplicity for low, which is necessary for low cost, simple regulation, and also high safety. It has to be very, very simple in order to be cost competitive, as has already been pointed out my friend Krister here, that you have to get rid of a lot of stuff that you have been used to in the past in order to keep the cost down. And I have chosen this 24 megawatts also for this very reason. that when I constrain myself very, very strictly with what I can produce, it puts limits on what I want to do and what I will be able to do. So I live in the hope that it will then serve as a defense against excessive requirements. What the reactor would look like remains to be figured out. It could be a vessel reactor, it could be a pool reactor, it could be a modular reactor. So there are many ways of setting up, as we've seen in the other presentations. And this is how it could look like. This is just the first sketch. But this is how we have been sketching this. Grade level would be somewhere around the roof. Energy efficiency for a pure heating reactor would be like 100%. We would need some electricity to run some, maybe run some pumps and so on the plant, but the energy that we put into the plant motor actually gets converted into heat ultimately, and heat is what we sell. So we can say below grade siding helps with external threats. Unmanned operation should be possible, so remote operation from the headquarters of the owner. Scalable modular design, standard industrial components, standard industrial heat exchangers, for example, and valving and so on. We need to design this so that we need a very, very small amount of equipment in higher safety classes. So minimal amount of safety classified system structures and components. We can't get rid of having some. We will definitely need safety class 1 fuel cladding, for example, or fuel rods, but not much more. Not much more. So it must be inherently safe, secure, also proliferation resistant, obviously. Security reasons prevent me from showing you how to get in there. As you can see, this is underground and there has to be an access route, but you know, can't show everything publicly. Safety. The safety thinking for large reactors has evolved over the decades, is based on the defense in depth principle, and it has gotten quite complicated. And we have in theory, in IAEA, safety requirements for system design, which have then been carried over to VENRA harmonized requirements for future reactors. Safety objectives, I think they are called, for future reactors. 5 different levels of defense are stipulated, but when you look into how these are implemented in real life for the different safety functions like criticality control, heat removal and containment of radioactivity, you will find out that same systems are credited for multiple defense lines. Sometimes there is nothing that you credit, sometimes there is a dedicated system. But in truth, you don't have 5 independent lines. You just don't. And if you look into equipment, it gets even worse. So you credit the same equipment through all the lines. Same control rods, for example, same containment structure, to name a few things. The same reactor vessel. So in reality, what you have is 2 or at most 3 separate levels of defense. This we can implement in a simplified reactor very easily. In the FinReactor, the Suomi-reaktori, we would have the operations done by simple systems. So we need something that we can control it so that we can bring the reactor online, and we can control the follow the load if need be, shut it down when we want, and so on. And safety, I want to rely mainly on inherent processes in the system. So no safety systems, inherent processes. So which means that the reactor system has to be configured so that I can show that, okay, I can shut it down at will. It will shut down itself if something goes wrong, and it will give away its heat even if my operational systems don't work, so that I can get rid of the heat. A bit like Christer was describing, that we rely very, very much on what happens inside the reactor. And then there is a part where exactly that would be located, I don't know yet, but there is a part where we can practically exclude some things. And I want to mention this because people tend to forget that there is a long list of practically excluded events in the large reactors as well. Okay, there is quite a bit of things that have been practically excluded, and we should be able to follow the same reasoning and be able to practically exclude some events. Whether it's the melting of the core or not, I don't know. This we have to discuss in the light of concrete examples together with the research community and the regulators and the industry. But basically, practical exclusion is feasible whenever you can show that some things are physically not possible. Okay, so small loads, high capacity structures, for example, is one way of arguing for practical exclusion. It's not the only thing, but it's one easily understandable way of doing this. In order to get this done, as has been discussed already earlier today, this takes a bit of revamping of the nuclear licensing practices and nuclear regulation practices so that we enable cost-effective deployment of this technology. And on the licensing side, we need to move from this one-off practice that there are massive mega projects that are licensed once, and then those who survive are happy to never try again. And also for the practical implementation and operations oversight, that has to be made a little bit more practical than it is today. And like our ministry representative was pointing out before lunch, some of these things have been thought out already. So for example, this is the licensing process, also shown by Minna, and no need to go deep into the details now. No, come on. Sorry about that. Yes, and the elements that are needed, the new elements, we already know roughly what they are, and it just remains to they just remain to be written in the law and detailed and justified, and the bit of political process. But I come back to my earlier point that in past history the ministry has been at times very creative in interpreting the nuclear law. So I hope that this could happen again, so that we could, in the context of the present law, even already initiate some activities to this end. The purpose of the law and the purpose of regulations is to enable things. Okay. This is very, very important. The law and order and regulations and controls that we have are there to enable things to happen. Right. So this brings me to my conclusions on Suomi-reaktori, or the FinReactor. We are developing this 24 megawatt thermal low temperature heating reactor. We believe that these district heating reactors would be immediately feasible in Finland, and they would offer major climate benefits. And this would also, such a development, such a concept would be an optimal vehicle for involving the Finnish industries in more concrete discussions on who can do what and what can be practicably done to guarantee certain properties for all the equipment, adequate properties for all the equipment and so on, and supporting a licensing and regulations update. So with that, I thank you for your attention.